This is Chapter 17, Section 1. We're going to look at the reaction process. We'll talk about a little bit about reaction mechanisms, activation energy, and then how to calculate that activation energy. I will go through most of these slides pretty quick because a lot of them have definitions that you're going to need to write down. So without me highlighting too much besides the super important parts, just make sure you get everything written down within your notes. So it states right here, the different reactions that we have can occur at different rates, and we will look at the speed or rates of these reactions today. In this example right here, if we look at the reaction mechanism, it is a step-by-step sequence of reactions to get to your overall chemical reaction. And the overall chemical reaction there in yellow is showing you how hydroiodic acid is made, or hydrogen iodide. You got your hydrogen gas and iodine that are reacted together to give you HI. But to get through that, we do have intermediates within the reactions, so it isn't just a one step gives you the last step. We do have some one or more other possible middle steps within these reactions. If you had a homogeneous reaction, though, your reactants and products would exist in a single phase. So as I'm looking at this, so the formation of HI, here is one possible mechanism to that. You would start off with iodine, that's in its diatomic state. You would break it apart into two iodine atoms. Those atoms would immediately react with hydrogen that was introduced, and that would form HI. So if you cut out your intermediates, which are the two I's, you end up with your final reaction there. Another possible mechanism that you have is a three-step one. Notice the first step is the same, but in this case, when you took your two individual iodine atoms, you could react them with hydrogen, but this time, instead of it going straight to HI, it would give you H2I, which in turn is reacted with the other iodine atom from the first step to give you two hydroiodic acid molecules. Again, intermediates here would be blocked out, and you would have the same overall reaction mechanism or reaction as you do in the other option. So like it shows you, your reaction intermediates will not appear within the net equation. Now we're going to move into, well, how would we know which of these set of mechanisms would actually produce HI? We're going to get into collision theory. So again, there's collision theory talking about how do your reactants collide with each other to give you the molecules that you want. You have three options here. In the first one, it says the collision is too gentle, so notice there's not a reaction. In the second, there's poor orientation, so again, you don't get the reaction you're looking for. But in the last one, you have effective collisions and correct orientation and energy, so that reaction will take place. Again, you're writing this down right here, but it's just reiterating what you just saw. In this one right here, it's showing you several options of orientation and maybe the speed at which molecules are moving. That will not give you an effective collision, but the one there at the top that is not marked through in red would give you a correct collision orientation and rate to make that happen. So the two different reasons why a collision might fail, again, if there's not enough energy or if you are not oriented properly. Moving on to activation energy. In this one, if we talk about the production of water between hydrogen and oxygen gas, it normally does not occur spontaneously at room temperature. The bonds of these species have to be broken in order to form new bonds, so your hydrogen and oxygen must be broken apart. And bond breaking is an endothermic process, where bond forming is an exothermic process. So this last part right here is going to be especially important once we get into some of our graphs. So the definition for activation energy, it's the minimum energy required to transform reactants into an activative complex. You do have an initial input of energy needed to overcome any repulsive forces between your reactant molecules, and that initial energy input activates the reaction, so you will look at how to calculate activation energy. So in this example right here, the decomposition of HI, if we look at just the general activation energy, some things of note whenever we do get into our calculations. Notice that your initial energy is here. It does give off energy here. And then notice it drops back down. Your products are below the initial energy for that reaction. Whereas in the decomposition of HBr, notice you have an initial amount of energy, you have your activation energy here, but then your products, that energy is above where you initially started. So we will get into what does that mean for our calculations. I would make sure I get these within my notes too. And this one right here, just breaking it down, this is showing you potassium plus water. And our products are going to be potassium hydroxide and hydrogen gas. Notice for our enthalpy, which we've got our forward mechanism here. Forward mechanism here for our activation energy. You can see the exothermic process there. But then as we move down, we have our products over here. And again, this energy is going to be below where we initially started. And that change that you have right here, that is your enthalpy of reaction. We looked in the previous couple chapters on how to calculate that. So it's a negative 393 kilojoules, and that negative means we are going to have an exothermic reaction. So the forward reaction here is exothermic. The reverse reaction, if we had to reverse, would be endothermic. Couple more definitions. Your transition state, it is a brief interval. It's where we break and form our bonds. Activated complex, you have your structure that results from an effective collision, and that persists while old bonds are breaking and new bonds are forming. So that's called an activated complex, and these are short-lived. In this example right here, we've got a couple different activated complexes. This is when we were forming our hydroiodic acid. But if we look, starting with our iodine here at the very beginning, so this first complex, that's where we were trying to break down our iodine. In this next one, if we are taking what was produced and adding our hydrogen to that, again, if that actually produced the H2I and we add our other iodine atoms, so this is going to be that second reaction mechanism that we looked at with HI. And then in that last step, actually forming the product that we want is going to be that last step. And notice that is the highest activation energy that you see there is going to be that last step within each of these. So as I look at this right here, the KMT states that the speeds and kinetic energy of molecules increases as temperature increases. We did learn that back already. So again, as temperature increases, speed of your molecules do. These collisions will have enough energy to form an activated complex, or a reaction will not take place. If you raise the temperature of reaction, it'll provide more molecules that have the necessary activation energy and cause an increase in reaction rate. Now we're going to go look at an example. I might add a second example too. In this first example, just know that that is the wrong graph for what we're going to do right now, but we will come back to it. I'll redraw the one I want you to use. But we're going to copy this energy diagram in your notes, and then here's the things we're going to label. We're going to label reactants, products, delta E or change in energy, EA that is going to be for from the reactants itself where we start to our peak. EA prime is from the peak to where the products are made, and then we will determine the value of the forward reaction, that much energy, the reverse reaction energy, EA and EA prime. So let me go give you the actual graph we're going to use to do all of these, and then we'll come back and look at this one. So this is the graph we're actually going to use for this first example. And again, there were several things it wanted us to label. The first was label the reactants and the products. So our reactants are over here on this end, and products will be on the opposite end. It also wanted us to label the change in energy, EA and EA prime. So EA, that is going to be your difference between your reactant energy level and the peak in the curve. So here's our reactant energy level, and then the peak of the curve is all the way up here, so this is labeled as EA. EA prime is the difference between the product energy level, which is right down here, and the peak in the curve. So EA prime right up here. Change in energy, that is going to be the difference between where we've got our reactants and our products. So change in energy right here, delta E. And now it wants us to go back and determine the actual values for the forward reaction and reverse reaction, how much energy is involved, EA and EA prime. So let's go look at those. If I look at the forward reaction first, oh, and by the way, we're supposed to label forward and reverse reaction. Those are already on here. So delta energy for the forward reaction, that needs to be the energy of our products minus the energy of our reactants. If I go look at numbers that are right here, the energy of my products is right at 50 kilojoules, and energy, I'm not going to write kilojoules per mole, but you can go and put your units in there. And the energy of the reactants is actually down there at 0. So for the forward reaction, the change in energy is a positive 50 kilojoules per mole. Now, change in energy for the reverse reaction. For the reverse reaction, you're just going to flip it. It is your energy of your reactants minus the energy of your products. So that is now 0 minus 50, and that is a negative 50 kilojoules per mole. Kilojoules per mole. It wanted us to find EA. So that's the activation energy of our reactants, essentially. And that activation energy there, it should be the energy of your activated complex minus the energy of your reactants. So as I look at those values, the energy of our activated complex is up there at 80 kilojoules per mole. Our reactants is 0, so that is a positive 80 kilojoules per mole. And if I look for EA prime, that is the energy of our activated complex minus the energy of the products. So that would be 80 minus 50, which will give us a positive 30 kilojoules per mole. So that is this particular one. Let's go back and look at the actual picture that they gave us in the sample, and let's work through all of that. So if I were to use this one and I were to actually put labels on it, EA, we would have this as our, just a second. Okay, back with you. So EA here, sorry about that. We have this right here as EA. EA prime would be this area. And our change in energy, I'm going to draw it on this side just because I got more room for our change in energy there. So that arrow probably shouldn't go quite all the way down below that. It really stops about 125. And I'll give you some better values too, because I know that scale is pretty wide. So change in energy here. We have our forward and reverse reactions. If we were to calculate the forward reaction here, let's say that the top of this right here is really, I would say the book's got it as 86 kilojoules per mole, and this very bottom part, you can tell it starts at 0, but the bottom part is around negative 125. It might be right there on the negative 150. Let's see. We're just going to keep it simple. Let's just keep it simple. We'll leave that as 100. We'll leave this as negative 150. So EA for our forward reaction, that is going to be energy of our products minus energy of reactants. So that's negative 150 minus 0. That leaves us as negative 150 kilojoules. Change in energy if we're looking for the reverse reaction, that is energy of reactants minus energy of products. So 0 minus a negative 150 is 150 positive kilojoules per mole. EA looks like it is going up to the 100. So that is your energy of activated complex minus energy of reactants, which would leave us as an answer of 100. And then for EA prime, if I looked at it, it's energy of activated complex, which is the 100 minus the energy of products, which is negative 150. So if you take 100 minus negative 150, you get a positive 250 as your answer for EA prime. If I asked you in this one right here, is the forward reaction shown in the diagram exothermic or endothermic? The forward reaction is exothermic. Exothermic here because the energy of reactants is greater than the energy of the products. So energy of your reactants is greater than the energy of your products.